You. Oh,
No, I thought Jalen was sharp.
Chase, you should have these notes. So, I don't see anyone that hasn't been present when I handed these out. We were building some skills at learning how to analyze force problems. We were learning how to create free body diagrams and use them to create a net force equation. And you will always, always, always use this kind of a process. If you have a force problem, you will always want to draw out the forces first and then use those forces that you have on your drawing to create a net force equation. And then the net force can only be equal to one of two things. If there is no acceleration, it can be equal to 0 newtons. If there is an acceleration, it's equal to mass times acceleration, right? So those are our only two options. And then we equate whatever that is to the sum of forces, and we use that resulting equation to solve the problem. Okay? Now, in this one, we finished the one before that, right? I think we were just starting to talk about this one. In this one, the rocket blasts off and its vertical velocity increases with time, or at least you guys should. You should get out your other notes, not these new notes, right? No, I did not collect these. And I think I asked if anybody got an actual answer for the height to which the rocket climbed, but it seemed like an excessive amount. So we'll see if we can figure out what went wrong.
123,750.
Right, okay, and that's about 100 times the height to which it actually climbed. Well, and actually, you would have needed to have known what the mass of the rocket was, and I hadn't given you that information yet. So it's my fault partially, or mostly actually.
I was like, partially.
Yeah, mostly. Okay, so what contact forces were present related to the rocket? Okay, air resistance and thrust. And then what non-contact forces? Gravity. Okay? So it's a pretty simple thing by now. You've done this several times, and the only thing that's going to be in the upward direction is what?
Thrust.
The thrust, right? And so we're going to say, and I'm just going to call this a force applied. You could call it force T or force thrust, whatever you wanted to call it. I'm just going to call it an applied force. And then we had a very small force due to air resistance. I'm just going to call that force drag. And then we had some gravity to go along with it. And make sure you understand that it's accelerating in the upward direction, so whatever forces in the upward direction are present have to be greater than whatever forces are present in the downward direction, right? If I'm going to draw this correctly, I need to show that. And then I was told that we had a force of 935 newtons for thrust and a force of 45 newtons. Is it 45 newtons for drag? And then 615 newtons for gravity. And actually, I didn't need to give you the mass. You could figure that out on your own. Okay, so, and we also know that the force due to gravity equals mg, right? Mass times the acceleration due to gravity. Okay, so in this scenario then, I'm accelerating, so if I write out my net force equation, I don't have any choice. The next thing I put down has to be ma or 0. Since I'm accelerating, it's got to be ma, right? Okay? I don't have any choice. That will always either only be 0 or ma. And then the sum of forces. And I'm going to subtract the opposing forces from the force in the main direction that's the main force here that's causing the acceleration. So I'm going to say, and I want an equation first. I don't want numbers yet. So FA minus F drag minus, and I'm just going to go ahead and put mg here. And this is your net force equation, right? The net force equals mass times acceleration. It always equals mass times acceleration. And if there is no acceleration, then it's 0, right? And then this force minus this force minus this force. Okay? Now, what is it that I've been asked to find? What is it that I've been asked to find? I've got a motion problem, don't I? I don't just have a force problem, I have a motion problem as well. I've been asked to find the height. And have I been given a certain amount of time?
30 seconds.
Okay, so I can't use v squared equals v0 squared plus 2a times x minus x0 to find that, can I? Is this a problem with acceleration or constant velocity? Acceleration, right? So I can't use x equals x0 plus vt to solve that problem. Okay? Do I have a final velocity? No. So I have to use x equals x0 plus v0 times time plus 1/2 at squared to solve this. And you can leave it as x if you want, or if you recognize that this is in the y direction, y equals y0 plus v0 times time plus 1/2 at squared. You can write that out like that as well. But this is the equation that I'm going to need to use to find how high it goes, right? Now, if I needed to, I could also write out a motion diagram. I'm not going to in this case, but if I needed to, I could. But I'm going to recognize my initial height, y0 is 0. My initial velocity, right when that rocket first starts moving, it's got a 0 velocity, right? So y equals 1/2 at squared is what I'm going to use to find my height. Now, this brings up a question. If you've got a problem where you've got a force problem and a motion problem, where do you start? Do you start with the motion problem or do you start with the force problem? I started with the force problem here because that's what we're talking about, forces. But normally, if I was asked to find the height of the rocket after 30 seconds, I would start by creating a motion problem. That's what it is, right? In essence, this is a motion problem. How high does it go? Okay, so I probably would have started out with this if I was doing this on a test or somebody asked me to solve this problem, because that's what I need to find. And I would find y equals 1/2 at squared, and then I would be like, oh crap, I don't have acceleration. How am I going to find acceleration? Oh, I can find acceleration if I do a force problem, because acceleration is part of both motion problems and force problems. And acceleration will be the thing that connects those two. Energy gives rise to forces, which give rise to motion. And the way she said that, motion, like God, please stop saying that.
More sauce if you want me to.
That's all right. Please stop saying energy gives rise to forces, which gives rise to motion. But that's the way it works, right? And it's acceleration that connects those two things. So I would realize I don't have acceleration, and then I would go solve my force problem. Now, it's all up to you, right? You may be good enough at this that you recognize right away, hey, I'm going to need to solve this force problem, so I'll just go ahead and solve that first and have the acceleration available to me. In general, I will write down a formula that answers the question that I need first, and then inspect it, and then go do another problem if I need to. So anyway, I want the acceleration. This tells me how to find it, right? I need to say A equals FA minus F drag minus mg all over m. Okay? Now, I realize that I have m here, but I don't have m in these two things, so I can't get rid of the m that way. I'm going to have to solve yet another problem because I don't have mass. But I know how to find mass, right? I know that mg, and I'm just going to come over here and say this, mg equals 615 newtons. So mass equals 615 newtons divided by 9.8 meters per second squared. If somebody would be so kind as to divide 615 by 9.8 for me.
62.76.
So we'll say 62.8 kilograms. Okay, so now I've got a mass. Now I can go ahead and say my force applied was 935 newtons minus my force due to drag, which was 45 newtons, minus the force of gravity, which was 615 newtons, divided by 62.8 kilograms. And you'll get lots and lots of practice at this. This is not going to be something I just leave you hanging with for, what'd you get?
4.4.
4.4 meters per second squared, which is cool. I can go back over here now and say 1/2 times 4.4 meters per second squared times 30 seconds squared. So 900 times 2.2. I'll just let you figure that out. What'd you get?
1980. Well, 1980.
1,980 meters. Okay, so after 30 seconds, the rocket's only 1,980 meters. Okay, that's about a mile up. Okay, that's pretty consistent with what you know of rockets, right? It takes a while for them to get that acceleration going, and you know, after about 30 seconds, maybe it's a mile up in the air. Okay, so the pattern of activity. I ask myself, is this a motion problem or is this a force problem? If it's a motion problem, I write out a formula that will solve my motion problem. And if I need to, use a motion diagram. Go through the process, x0, x, v0, v, and acceleration and time, and then figure out what formula you need to use and write it out, and then inspect it and say, wait a minute, I don't have acceleration. Okay, and then say, oh, I can use this force setup to find out what the acceleration is going to be. We did that. We created our free body diagram. Our free body diagram showed us how to set up the sum of forces, and then I isolated acceleration, plugged my values in, found that. Along the way, I recognized that I also needed to find the mass of the object because I needed to plug that in here, and we solve the problem. Okay? So life is just a strategy, right? That's my saying. Life is just a strategy. And you want a strategy that will allow you to accomplish everything, right? This is our goal. We're trying to create strategies that never fail, that always work. And when you come up against something that you aren't quite sure about, you follow the strategy and it will lead you through the problem. Any questions about this particular problem? Okay, so hopefully that makes sense. So, we need to start talking about Newton's third law of motion. Newton's first law of motion says, I don't like to have my motion changed. But if you change my motion, you need to use a net force. The second law says, this is how much force you need to use. And then the third law explains an observation that we're sort of familiar with, but will also give rise to a lot of confusion. So, consider the following description of a portion of the science fiction short story Marooned Off Vesta by Isaac Asimov. This was the first story he ever published in the 1940s. He was 18 years old at the time, after which he became the greatest science fiction writer of all time. That's my opinion. Several spacemen are in a small portion of a spaceship that's been cut to pieces by a meteor. Their air is running out. They're near a planet that could rescue them if it was known that they were there, but they had no radio and seemingly no way to get near enough.
So, was that written before or after David?
Huh?
Before, right?
Yeah, before. So did he get a? Okay, that's today's. So a long time before Dune, actually. So they were outside the planet's gravitational pull. Then suddenly one of them gets a bright idea. The portion of the spaceship where they're at has a water tank attached to it for use with showers. The water is under pressure, and if a small hole is poked in the side of it, water will escape at a high velocity, acting as a jet. The ship will accelerate in the opposite direction towards Vesta, and they were rescued. So the situation describes Newton's third law in action that states when an object exerts a force on a second object, the second force exerts an object on the first that is equal in magnitude but opposite in direction. And the two forces together are known as action, reaction forces. One force, the force applied, is the action force, and the reaction force pushes back. The pair of forces is known, not surprisingly, as an action-reaction pair.
Can I get one of the new ones? I'll be back here.
I thought you got one. Oh. Is there one more over there? So, you've probably heard this stated: for every action there is an equal and opposite reaction. Okay? In the story, the stranded spacemen use this principle to create a force in the direction opposite the one they want to go, knowing that the reacting force will push them in the direction they do want to go. Another often quoted situation where this law applies has an individual stranded in the middle of a frozen pond. Knowing that ice can be virtually frictionless, the individual takes off a boot, throws it in one direction, knowing that the reaction force will drive him in the opposite direction. Okay, so there are lots and lots and lots and lots of examples like this, and it's really, really intuitive that if you push against something else, if you're on wheels or you're on a frictionless surface, you'll go in the opposite direction. But this also creates a great deal of confusion for us because we're not paying attention to where our forces are applied. So apparently there was a horse that learned Newton's laws. And when it was told to pull the cart, it refused saying that if it pulled the cart forward, according to Newton's third law, there would be an equal force backwards. Thus, there would be balanced forces, and according to Newton's first law, the cart would not accelerate. Okay? And that sort of makes sense to us, doesn't it? It's like, yeah, the horse has got it right. If I pull on the cart's going to pull back on me with the same force, and we're not going to go anywhere. But you obviously know that that's not true, because we have all kinds of situations where the horse pulls a cart and it goes wherever we want it to go. So we have this confusion here, and so there's something that's just not quite right about the horse's argument. And the confusion usually arises because we don't take a close enough look at all of the forces involved and where they're applied. So let's make this a little more general. And we're going to consider how any object moves by contact with a surface, whether it's a car in contact with the road, our feet in contact with the ground, or the horse in contact with the ground. So we've previously only considered forces that have been acting on an object and not forces the object exerted on its surroundings. When we also consider how the object interacts with the surface it's in contact with, we need to recognize we haven't been very accurate when we describe the forces involved when we talk about the forces that give rise to acceleration. So we might have previously talked about how an applied force gives rise to an acceleration of a race car. And we think about it, and it's like, well, the race car has this engine, and the engine applies force to the wheels, and that's what causes us to go forward. But that's wrong. That's not really true. It's not entirely accurate. And if you think about it, the actual point of contact of the car tire with the road, the applied force from the engine causes the direction of the motion of the tire to be backwards, right? If the tire is spinning in this clockwise direction here, where the tire reaches the road, the tire is actually moving backwards. How does that cause us to go forward? So if the actual motion of the tire is at the point of contact in a backward direction, it doesn't make sense that this is what's actually causing us to move forward. So what we now need to realize is that because of the friction force between the tire and the road, the backward motion of the tire at the point of contact creates a friction force on the earth, right? Friction force is backwards. Okay, the force of friction of the tire on the earth. Okay? And this will cause the tire to accelerate, or would cause the earth to spin backwards, wouldn't it? If I had a car here and it was big enough, might we actually be able to cause the earth to rotate in the opposite direction? And we'll talk a little more about that in a minute, because that doesn't make sense, does it? But anyway, this would be the action part of the reaction pair. The tire is pushing on the earth in a backwards direction. The surface of the road exerts an equal and opposite force on the tire. Okay? So it's not that the car is causing itself to move forward. The earth is actually pushing the car. Okay? The reaction force of this is what's causing the car to move forward. Or if I'm running or walking along, I'm pushing backwards on the earth, and the earth is pushing forward on me. That's an equal and opposite kind of situation. Okay, so I don't know if you've ever thought about it in these terms before, but in order for us to truly understand the nature of this kind of acceleration, we have to think about where the actual force is occurring. In any situation where motion occurs related to a force that's exerted on a surface, whether it's a bicycle or a trax train or running or anything like that, we're creating a force on the surface due to friction, and the surface is creating an equal and opposite force on us. Okay? So, although the engine creates the spinning of the tire that caused the backward force on the surface of the earth, the force causing the car to accelerate is not the force generated by the car engine, but the reaction force of the friction on the road on the car. Okay? Now, here's where we figure out that this doesn't mean that the thing isn't going to move. Okay? According to Newton's third law, these forces are equal and opposite in direction, but they don't cancel each other out because they're not acting on the same thing. The earth is acting on the car, and the car is acting on the earth. These forces don't cancel each other out. They would only cancel each other out if they were both acting on the car. That would keep the car from moving. But the earth acting on the car is not the only force around. Okay? There might be other forces acting on the car. If you're considering whether or not the car actually does accelerate, only forces affecting the car can be considered. Okay? I don't care that the car is pushing backwards on the earth. I've got my car here, and the earth is pushing forward on the car. Forces that would modify this force would be affecting whether or not the car accelerates. Okay, so let's think about what other forces might be acting on the car. And so we're going to call this the force of friction on the car, right? The force of friction on the car. But maybe I have air resistance acting in a negative direction. Okay, but it's not going to be that great compared to this force. So if that's all that's happening, because the force of the earth on the car is great enough in overcoming the force of air resistance, then I'm going to accelerate. The presence of friction acting in a negative direction on the car. And this is weird because, wait a minute, we've said that the force of friction is acting in a forward direction. The earth is pushing the car. Yeah. Sure. What would happen, though, if we were driving in mud or if we were driving in sand? Would I also not get a friction due to the mud or the sand in a backwards direction, preventing the car from going forwards? Okay. The presence of a brick wall. If I've got a brick wall sitting here, okay, it doesn't matter how much force the earth is pushing the car with in a forward direction, the force of the brick wall is probably going to prevent that from going forward. Okay? A tailwind. Actually, that would give us more force, wouldn't it? It would give us more force in the forward direction. Or maybe a rocket pack would also give us more force. The point is, these two forces, the force of friction from the car on the earth and the force of friction from the earth on the car, are not canceling each other out because they're not acting on the same thing. Only the force of the earth on the car is acting on the car. The force of friction of the car on the earth is acting in the opposite direction, but it's acting on the earth. So all of these things would provide additional forces that would go into determining whether or not there's ultimately a net force that would cause a positive acceleration, regardless of the fact that there is an equal and opposite force of the car on the earth. So the horse does not understand what's going on here. He's exactly right in saying that if I pull on the cart's going to pull back on me with an equal and opposite force, but it doesn't matter because that's not a force that's acting on the horse. And you get into all kinds of alliteration problems or rhyming problems here when you talk about the force of the horse. And I'll mix my words up probably. Now, according to Newton's first and second laws, how much acceleration is caused by the force depends on the mass, or more accurately, on how much resistance there is to acceleration because of the mass that's present. So in mathematical terms, we say the acceleration that occurs will equal the force divided by the mass. So that acceleration will equal the force divided by the mass. So in the car example, we can look at this from the perspective of both the car and the earth, and this will pull this all together. We've said that the force of both the action and the reaction pair will be equal. Let's say that the force applied by the tires on the surface of the earth in the negative direction is 3,000 newtons. Okay, so let's say that here's the point of touching the tire with the surface of the earth. And we'll say that there's a force on the earth from the tire of 3,000 newtons. Okay, so there will be a force on the earth from the tire of 3,000 newtons. Okay, there will also be a force on the, and let me make it the same length here, force of earth on the tire of 3,000 newtons. Okay? It doesn't really matter what this force is, the backwards force. The forward force on the car is going to also be the same. So, negative direction is 3,000 newtons. Therefore, the force applied by the surface of the earth on the car is also 3,000 newtons. We know that the car's mass, let's say, is 1,000 kilograms, and we know that the earth's mass is 5.9 times 10 to the 24th kilograms. Yeah. If we consider no other forces on the car, this 3,000 Newton force will accelerate the car in the positive direction by 3 meters per second squared, right? Acceleration equals force divided by mass equals 3,000 newtons divided by 1,000 kilograms equals 3 meters per second squared. Okay? If we consider no other forces on the earth, this 3,000 Newton force will accelerate the earth in a negative direction. 3,000 divided by 5.97 times 10 to the 24th kilograms gives me 5 times 10 to the negative 22nd meters per second squared. How much is that acceleration going to affect the Earth's rotation?
Huge.
Yeah, huge amount, right? It's not going to affect it at all, is it? So, what I've said is if you want to actually think about this, and the thought occurred to me, well, if one car can affect the acceleration of the Earth in that way, how many cars would it actually take all doing the same thing to cause the Earth to go backwards? Therefore, it would probably take about 1 times 10 to the 21st cars lined up on the same longitude line on the Earth, all accelerating at the same time to provide enough force to perceptibly accelerate the Earth in a backward direction. That's kind of a cool thought, right? Let's go out and get 100 quintillion cars and line them up along the same line of the Earth, right? It's all there. And then have them all accelerate at the same time, and we could literally turn the Earth backwards.
Are there even that many cars?
No, there's not that many anythings except atoms. No, there's not that many cars. I don't know, maybe there's 1 billion cars on the planet. 10 to the 9th. Okay? Is this making any sense at all? That we have this point of possible confusion, but that it's not really the case, right? The whole answer to that confusion is the action and reaction force are applied to different objects. They don't cancel each other out because they're not applied to the same object. Okay, now, fortunately for us, many of our problems will not deal with needing to look at action-reaction forces in this much detail. If we are just considering forces causing the acceleration of something like a car, we'll still use the term applied force to indicate whatever force it is that's causing the forward motion. I don't really care whether it's the engine or the tire or the earth that's pushing on the car. There is an applied force that's causing the car to accelerate. However, in the back of your mind now, you should still recognize that this is not entirely accurate, and it's the reacting friction force generated by the road on the car that's causing the forward force. Okay? Now, the same thought process must also apply to situations where motion of anything results from contact between two surfaces. And so if we go back and look at the horse problem,
Oh, wow. Oh, you're talking about the unicorn.
okay, it's not a unicorn. Is that better? It's not a unicorn.
Oh.
How about we make it a unicorn?
Okay, so if we go back and think about this and consider why the horse is wrong. And consider why the horse is wrong. Okay, the horse exerts a force, the force of the horse on the cart. Okay, the horse is pulling on the cart. Okay, and the cart is pulling on the horse with an equal and opposite force here. That should have been a little longer, shouldn't it? So this is the force of the cart on the horse. Okay? So horse is pulling on the cart, cart is pulling on the horse. This does not mean these forces cancel each other out, because this force is not acting on the same thing as this force is. What we're going to have is another force in the opposite direction, right? The force is going to push, or the horse is going to push backwards on the earth with a friction force, and the earth is going to push on the horse. Okay, so the force of the earth on the horse is going to be greater than the force of the cart in the backward direction, so the cart will still accelerate. Okay, now, what kind of forces are acting on the cart other than the horse? Huh? What do those words mean?
What are the words?
Force of the horse, force of the cart, force of the earth. Okay? Now, what forces are going to be acting on the cart in addition to the horse? What's, huh? Okay. Related to the tires on the road, or also air friction, right? So force of friction in general. Okay? But the horse's pull is going to be greater than the forces of friction. It doesn't have anything to do with the fact that the cart is pulling on the horse. Okay? So this is how we avoid these things. Your response when you're presented with a confusing statement like, if I pull on something, something's going to pull back on me with the same force and nobody's going anywhere, should be, that's wrong. Because those two forces are not acting on the same object. That's your response. Those two forces, the action-reaction force, are not acting on the same object. Okay? So that's your response to that. And I'm going to cross out this section right here. Because we've already basically discussed all that. Okay? Okay, so let's try to use this. This is also going to be a problem for us in ropes. 65-kilogram boy and a 45-kilogram girl use an elastic rope while engaged in a tug of war on an icy, frictionless surface. The acceleration of the girl toward the boy is 3.0 meters per second squared. Find the acceleration of the boy toward the girl. Now, we have to do some thinking about ropes before we can deal with this. Consider a rope that's held stationary by forces either applied at the top and bottom of a vertical rope or to the left and right of a horizontal rope. I gave you some space there. So I've got a rope like this that's vertical. And I've got a rope like this that's horizontal. Okay? In either case, since the rope is not accelerating in either direction, the forces must be what? Balanced. Okay? So I've got a force here and a force here, and I've got a force here and a force here. Force, 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 force. Okay? So I've got forces. Rope's not accelerating, so the forces must be balanced, as indicated by the fact that all of the F's are the same. Now, because the rope holds itself together, there have to be forces throughout the rope that hold it together. Right? I've got a little particle here, and right next door I've got another little particle. And I've got forces pulling those particles in the opposite direction. So I must also have forces, and I didn't draw that very well. Let me draw that better. I have forces acting on these two particles, trying to stretch them, so I must also have a force acting this way on this particle. And I must have a force acting this way on this particle. And they all have to be balanced because there is no acceleration. These forces supplied are by the electromagnetic forces of attraction that hold all atoms and molecules together, or any solid together. So at either end of the rope, then, in either scenario, the force applied to the rope is countered by the rope in an equal and opposite fashion according to Newton's third law. Likewise, at each point or particle within the rope, we can consider equal and opposite forces to be occurring. So no matter where I'm at in this rope, there are equal and opposite forces occurring here. Okay? The result is that whatever equal force is being applied at both ends of the rope is also being transmitted uniformly throughout the rope. So the force within the rope is called the tension, and it's equal to the force applied at either end, which, if the rope is not accelerating in either direction, is the same. Note that the tension is not the same as the sum of the two forces on either end. Okay, if I've got people pulling here. Okay, why is there so much chatter back there? And I've got one person pulling at this end. Okay? Okay, if I've got 3 people pulling here and 1 person pulling here, and this force is within the rope is called, if I've got forces applied at either end here, if the rope is not accelerating in either direction, it's the same. So no matter how much force I've got pulling at either end, if it's not accelerating, the forces are the same. Note that the tension is not the same as the sum of the two forces. What would happen to the rope if the force of tension within the rope was the sum of the two forces on either end? Suppose I've got 100 newtons applied here, and I've got 100 newtons applied here. But if the force at any point in the particles in here was the sum of those two forces, okay, if I've got forces of 200 newtons going that way and forces of 200 newtons going that way on this particle here, what would happen to the rope? It'd rip. Okay, so the forces everywhere along here are 100 newtons. Okay, I've got a 100 Newton force at this end. I've got a 100 Newton force at this end because they're balanced and not accelerating. And everywhere else in between here, I've also got forces of 100 Newtons. Okay, there is no sum of those forces. The rope would tear. Okay? So, since we know whatever forces are present on the rope are immediately transmitted throughout the whole rope and immediately reacted on by the rope in the opposite direction, the identical reaction force must always be felt at both ends of the rope. Therefore, the force of the rope applies to the boy must be the same as the force that applies to the girl, even if the forces are different. However, because of the differences in masses, their accelerations will be different. So let's look at this here. So we've said, what did we say our 65 kilogram and 45 kilogram boy or girl? Okay, so I've got a 65 kilogram boy and a 45 kilogram girl. And they're holding a rope. And the forces, we've said, at both ends must be the same, because the forces that are transmitted throughout the rope are action-reaction forces. The force that both of these individuals feels pulling on them has to be the same. Okay? Despite the fact that this person is larger and maybe stronger than this person, the force that they feel from the other end of the rope is the same. The force of tension here equals the force of tension here. Okay? The force pulling on both of these is the same. Okay? They both feel the same force of tension. But that force is going to do more to this person than it is to this person because of the mass. Okay? So we've been told that this kid accelerates at 3.0 meters per second squared. Okay, and we want to know what the acceleration is here. Okay, so we know that force equals mass times acceleration, so that equals 65 kilograms times 3.0 meters per second squared, which gives us 195 newtons. Okay, so the force of tension on the boy here is 195 newtons. That means the force of tension over here must also be 195 newtons. But how fast is that going to accelerate the girl? Acceleration equals force divided by mass equals 195 newtons divided by 45 kilograms. Kirsten, how much was that?
4.3 repeating.
4.3 meters per second squared, okay? And that's what we would expect. We would expect this person to be accelerated faster than this person. It's the same force that's pulling on both of them. And this is one of the single most difficult concepts in all of physics, that this person is bigger and stronger than this person, but the force that they both feel at the end of the rope is exactly the same. If I have 10 people on one end of a rope and one person on the other end of the rope, the force that the 10 people would feel would be exactly the same as the force that the one person feels. It's just that that force is going to do a lot more damage to the one person than it is to the 10 people. Okay? So, forever now, as far as ropes are concerned, you know that the tension at both ends of the rope is going to be the same. And this will be important for us when we solve certain types of problems. One last problem here, and then we'll call it a day. As a baseball is being caught, its speed goes from 30 meters per second to 0 meters per second in about 0.0050 seconds. Okay? A catcher is catching the baseball, and the speed goes from 30 meters per second to 0 in about 5 thousandths of a second. The mass of the baseball is 0.145 grams. We want to know, first of all, what the ball's acceleration is. Okay? And that's a motion problem, right? So I'm going to go through my motion problem stuff. Okay? I'm going to think v squared equals v0 squared plus 2a times x minus x0. But I've been given time, right? So that can't work. I'm then going to think x equals x0 plus vt. But that's for constant velocity, and that's not going to work. I do have both velocities. And I've got a time, so in order for me to figure this out, I know I can use v equals v0 plus acceleration times time. And I know that v0 is going to drop out, and I know that the acceleration is therefore going to equal velocity over time equals, my final velocity is 30 meters per second. divided by 0.0050 seconds. So if I can get my calculator to,
Oh my.
I think it's going to be like 6,000 meters per second squared.
What's the bottom number say?
Or 0.0050 seconds.
Okay. 6,000.
6,000?
Yeah.
6,000 meters per second squared, and that's negative, right? Because the velocity, it's going to be 0 minus 30. So the acceleration is going to be negative 6,000 meters per second squared. Okay? What are the direction and magnitude of the forces acting on it? Okay, so then I have to draw a free body diagram so I can see what the forces are. Okay? Is there any force on the ball in the forward direction? Right before it hits the catcher's mitt, what forces are acting on the baseball? Okay, air friction and gravity. Let's assume that we're not really going to take those into account. Is there anything that's pushing the ball forward? Okay, but it's not a force anymore, right? It's just got a velocity. There is no force on the ball in the forward direction. There's nothing trying to accelerate the ball after it leaves the pitcher's hand, right? After it leaves the pitcher's hand, there's nothing that's trying to accelerate the ball. There is no forward force on the baseball. There's only the force of the catcher's mitt acting in the opposite direction. That would be an applied force. Okay, so what are the magnitude and direction of forces acting on the baseball? The direction is going to be that there is a force acting in the negative direction, right? And I want to know what that force is, and I know that I can create a net force equation, right? After I create my free body diagram, net force equals mass times acceleration. And the only force in my sum of forces, right? My only force in my sum of forces is that applied force. There is only one force. Okay? So that force is going to equal mass times acceleration, and that's going to equal, and I want to know what the magnitude of that force is. That's going to equal 0.145 kilograms, sorry. Times the acceleration, which is negative 6,000 meters per second squared. So if we could multiply 6,000 times 0.145.
Got 870.
We have 870, so negative 870 newtons. Okay, and it's not a negative number right here. It's 870 newtons in the negative direction. Okay, so the catcher applies a force of 870 newtons on the baseball in order to stop it from 30 meters per second squared, or 30 meters per second in 0.005 seconds. Okay? Now, what are the magnitude and direction of the force acting on the player who caught the baseball? My catcher that's not a very good catcher. There's my catcher catching the baseball. If the catcher applied a force of 870 newtons on the baseball, what force did the baseball apply on the catcher? 870 newtons in the opposite direction, right? So force on catcher equals 870 newtons in the positive direction. If he was standing on frictionless ice when he caught the baseball, would the baseball have accelerated him?
Yes.
Yes, it would have. And if that 870 newtons had been accelerating a 100 kilogram person, okay, if they had been accelerating a 100 kilogram person, it would have accelerated them at 8.7 meters per second squared. You don't need to write that down. I'm just adding that in there. But yes, it would have accelerated them. A better example of that might be a hockey player on ice. If they're not digging in with their skates and they catch a puck, the goalie catches a puck, that puck will literally cause him to accelerate backwards. Okay? Now, there's a lot of confusing things that we've talked about today, and we'll get lots and lots of practice over the next couple of classes practicing these things as we go through a bunch of different scenarios. Okay? And we'll actually conduct a little experiment. One of the things that we use this kind of information for to analyze problems for our elevators. We have an elevator outside our door here, and we'll try to see if we can't get some real data from our elevator in terms of how fast the elevator accelerates, and if you can detect that using a bathroom scale. So that'll probably be middle of next week. Okay. Any questions about the stuff that we talked about today? Okay. The rest of the time is